Very good afternoon to Dr. Ravindra Purwar.
Good afternoon.
And also very good afternoon to all participants of 1 week AICTE-ISTE sponsored 1 week induction program, which is based on the machine learning and pattern recognition. So on the behalf of SSBT's College of Engineering and Technology, Bambhori, Jalgaon, Maharashtra, I heartily welcome Dr. Purwar sir, Dr. Ravindra Purwar, who is the speaker of this session. Now, let me introduce Dr. Purwar sir. Dr. Ravindra Purwar has obtained his ME in Computer Science and Engineering from MNREC Allahabad. Currently, MNREC is known as MNNIT Allahabad. He has completed his doctorate degree from University School of Information Technology, GGSIP University, New Delhi. Dr. Ravindra Purwar currently working as a professor in the University School of Information, Communication and Technology at GGS Indraprastha University, Delhi. He has an academic experience of more than 19 years. He has successfully guided PhD students in the domain of image pattern recognition, multimedia security, and video processing. He is an active reviewer of various referred journals, transactions of the Springer, Elsewhere, and IEEE reputed journals. He is a life member of Computer Society of India, that is CSI, and he is also the life member of Indian Society of Technical Education, that is AICTE. So this is the brief introduction of Dr. Ravindra Purwar. He is such a high profile personality is among with us. So I request humbly Dr. Ravindra Purwar ji to start the session. Thank you very much, sir. Welcome.
Thank you very much. First, very good afternoon to all of you. I think
all the participants, please mute your mic. Gaikwad madam, please mute your mic. Now I request Dr. Ravindra sir to continue the session.
Yeah, very good afternoon. Am I audible?
Yes, sir. Yes, sir. Yes.
Okay. So I'm going to share slides before all of you. So is it visible?
Yes, sir. Yes, sir.
Okay. Right. So my dear friends, through this session, I will tell you some fundamentals of digital image processing, and then I will tell you an application of pattern recognition in medical image processing domain. So before coming to that application or that work in the field of medical image processing, let me tell you some basic concepts of digital image processing, though you might have read it about these concepts. Some of you may not be aware of this concept, so let me explain step by step. And I will use those concepts while discussing the application in medical image processing. So first point is, what do we mean by an image? We generally use different type of images in our daily life, daily routine. So point is, what do we mean by an image? So we can define an image like it's a two-dimensional function as fxy, and where x and y are the spatial coordinates, and the amplitude value at point xy is denoted by fxy. So this is called an image. And then what is the digital image? Digital image is basically an image which is discretized. Discretized in terms of its spatial domain as well as in terms of its amplitude. So if you look here, you can see here an illustrative example of digital image where we have different small squares which represent basically the spatial coordinates of points where amplitudes are being displayed or colors are being displayed. So you can say if xy, that is the spatial coordinate, and f, which is the amplitude, are all discrete values, then the image is called a digital image. Now, when xy and the amplitude of f are finite and discrete quantities, the image is a digital image. And a digital image is composed of a finite number of elements, each of which has a particular location and value. And these elements are referred as picture elements, or image elements, or pels, or pixels. So in this particular figure, you can say that this one represents the spatial coordinate, let us say 0, 0 with some intensity value. And the next is, let us say 0, 1. If you assume x-axis lying along the horizontal line and y-axis lying along the vertical line. So in some notations, in some books or literature, you will find that image is represented by using y information or y coordinates along x-axis, along horizontal line, and x coordinates along the vertical line. So it depends only on the convention which is used. For example, we have an image here, a child image, and the nose part, which is shown through a rectangle here, the corresponding values of pixels are shown here. So we can see here that we have a number of values associated with an image, and these values are called pixel values or pixel intensities. In this particular case, we are taking a grayscale image. Grayscale image means the image is not colored. Okay? So since it's a grayscale image, it means there will be only one intensity value associated with each pixel. And if I take here 256, for example, in this case it is a 256 grayscale image, it means the image intensities will vary from 0 to 256 minus 1, which is 0 to 255. If we take color image, then for each pixel we have 3 intensity values corresponding to 3 colors or 3 color component of the image. It can be red color, green color, and blue color. That is the RGB component. Now let us see some applications of digital image processing. So various stages or various steps are there, or various applications are there for digital image processing. Obviously, before processing any image, we acquire that image. So it is image acquisition. We perform image enhancement in the image, means we improve the quality of image, we remove some unwanted signals or information available in the image. We have image restoration. If the image is degraded, by using some degradation model, and if the degradation model is known, then we restore the quality of the image through image restoration. Image analysis, where you perform different type of analysis in the image. Image reconstruction, where we have different images of the same information from different point of view, from different orientations, and based on those orientations, we reconstruct the desired image or the image. Image compression, we have compressed the information present in the image for storage purpose or for transmission purpose. Image segmentation, where we segment the desired the desired content in the image, and we try to analyze that content. Representation and recognition means that here we define those segmented regions or the information within the image through some features, and based on these features, we recognize that image from either the database or from other sources. So, first point in digital image processing, as I told, the digital image is discretized in spatial as well as frequency domain, as well as in amplitude values are discretized. So, what is image sampling and quantization? The output of most sensors is a continuous voltage waveform, and to create a digital image, one need to convert the continuous sense data into a digital form. And this conversion involves two mechanisms to process. One is digitization of coordinates, that is called image sampling, and digitization of amplitude is called image quantization. So in the terminology of digital image processing, image sampling means we discretize the spatial coordinates, and image quantization means we discretize the amplitude values. So those who are from the electronics background or CSC background who have read the signal processing concept, they might be aware of this terminology. But here let us say we have a one-dimensional information or one-dimensional signal. So this is analog signal, and when it is converted into digital form, then this signal is defined on different positions, discrete positions, and that is called sampling. So you can say here, you can check here that these points have been identified at different locations. So it is basically sampling. And then the amplitude is also discretized. So these amplitude are described in terms of these values. So this is quantization part. So I repeat, any digital image has two steps. One is image sampling and that is image quantization. Next point is to understand what is the meaning of image size. As if you talk about the storage of image, we talk about different gray level, gray scales of an image. What is the amount of memory an image will require? So to understand it, let me take here an image of size, let us say m cross n. It means that there are m number of rows and n number of columns, or the image has been represented by using m cross n matrix. So there will be total mn picture elements or pixels. And if I assume here that capital L represents the grayscale value. Grayscale value means the image are permitted to have values from 0 to L minus 1. So if we say the general terminology, if I say that an image is, let us say, 256 grayscale image, it means the permitted values will be 0 to 255. If we say it is 512 grayscale image, the permitted value will be 0 to 511. Generally, L is taken as power of 2 for to reduce mathematical computation as well as to make it compatible with the storage phenomena. So if I assume L as 2 to power k, it means sometimes we also call that the image is a k-bit grayscale image, because to store L values, it will require total k bits of memory. So it is also referred as k-bit grayscale image. Now what is the storage? Since there are total mn pixels and each pixel will have values from 0 to L minus 1. It means the storage requirement for 1 pixel will be k bits, and since there are total mn pixels, so total size of the image will be m into n to k. This is the way how image size is computed. Now, if it's a colored image, rather it's a gray image or a grayscale image, if it's a colored image, then we have to multiply it by a factor of 3, because a colored image has 3 components: red, green, and blue. This is the way how image size is computed. Now we will discuss about some methods of image enhancement, because when we talk about the pattern recognition in the domain of images, then one very important step in pattern recognition is that we pre-process that image. And in pre-processing, we basically do some sort of normalization, where we may require to convert input image into some standard size so that it becomes scale invariant. We may require some sort of thinning operation where the skeleton of the image is preserved, but extra pixels are simply discarded, so that the quantum of information is not very confusing. We may require noise removal. We may require to enhance the quality of image. So these steps will fall into the category of pre-processing. And image enhancement is very important as far as pre-processing is concerned. So let us see the principal objectives of image enhancement. So here we process an image so that the result will be more suitable than the original image for a specific application. The suitableness is up to each application. So there are criteria for each application based on which we measure its suitableness. And a method which is quite useful for enhancing an image may not necessarily be the best approach for enhancing the images. Again, the enhancement methods depends on the type of input images. Now, when we talk about the image enhancement is done in 2 domains of images. One is spatial domain and another is frequency domain. In a spatial domain, basically, we have techniques that are based on direct manipulation of pixels in the image. Means in image enhancement in a spatial domain, we process the pixels or pixel intensities in the image, whereas in the frequency domain, we have techniques that are based on the modification of the transform of the image. And these transform may be cosine transform, discrete cosine transform, discrete sine transform, Fourier transform. So we work on the frequency domain of the image. Of course, there are some techniques which are basically the combination of these two, where we perform some operation in the spatial domain, others are in the frequency domain, or we may have a vice versa scenario as well. So we will discuss here in our in this session only the spatial domain in image enhancement technique, because the application which we will discuss later is basically it involves image enhancement in spatial domain. If you are interested, you can go for frequency domain as well. So in spatial domain, as I told, that we process the pixel intensities. So here we take an operator defined as T. So the general equation, or you can say general transformation that is used for image enhancement in spatial domain can be defined in this fashion, that here fxy is the pixel value at point xy, and then we apply some sort of transformation over this pixel value and we get the transformed image, that is gxy, or we get the transformed pixel intensity. So here fxy is the input image, gxy is the processed image or the enhanced image, t is an operator on f defined on some neighborhood of xy. So sometimes we take the concept of neighborhood where we not only consider the pixel intensity itself, we also consider the pixel intensities of its neighboring values. Just like in this figure, you can say the central point represents the pixel value, and we take here basically 8 neighbors in that pixel as well. It means these are the neighboring values. So first type of image enhancement is based on point processing. Point processing means we process pixel by pixel. So here the neighborhood size is just 1 cross 1 pixel, and G depends only on the value of f at point xy. So when such type of transformation is used, the notation is slightly like this. We define the transformed value of the pixel as S, and this is equal to TR, where R is the grayscale value of input pixel at point XY. So R is equal to grayscale of FXY, and G is the grayscale of GXY. For example, here we have a number of basically point processing based transformations. In this diagram, we have in fact total 3 type of transformations functions, where each again 3 type is divided into 2 subtype of transformations. Just like if you take a linear transformation or one type of transformation, which is point based transformation, is linear function or linear transformation, where we can have 2 types of images, or we can generate 2 types of images. One is the identical image, just like here you can see here in the x direction we have input grayscale, that is R. In the y direction we have the transformed grayscale, that is S. If you recall this equation, S is equal to TR. So the identical or identity transformation is nothing but y is equal to x. So this is the line with orientation of 45 degree. It represents an identical transformation. It means when there is no change in the pixel intensities, we get identical image, no change. Whereas a line with orientation of 135 degree or minus 45 degree, this one, this is a line for negative transformation. Again, it's a linear transformation. So here, whenever in the input image we have intensity value L minus 1, you see here that when we have L minus 1, the corresponding output image will have intensity 0. And similarly, when the input intensity is 0, then the output intensity is L minus 1. This negative images, that's why we call it a negative transformation, because by using this negative transformation, we generate negative images. So they are mainly used in the domain of medical image processing. Very important transformation in terms of medical domain. Also, we have different other type of transformations like logarithmic function, where we have log and inverse log transformation. If you plot these transformations, they may look like this. This is a log transformation. This is the inverse log transformation, you can see. Then we have power functions or power log transformations. So here, this is the nth root transformation, whereas the lower one is nth power transformation. So if I take one by one, as I told, identity function, output intensities are identical to the input intensities, no change in the intensity value as I. Negative images, as I told, that the transformation for negative images can be defined as S is equal to L minus 1 minus R. So it means when R is 0, the transformed pixel value is L minus 1. When R is L minus 1, the transformed value is 0. So the role is it reverses the intensity level of an image. If you took the advantage or one application of negative images. Here we have a mammogram image where there is some clot in this region, and in the original image the clot is not that much visible, or that it may not be that much clear, because one may lead when we have some sort of confusion by observing these regions as well. But if you take the negative image of the corresponding mammogram image, the clot is very much visible and clear. So that's the importance of using sometimes negative transformation. Next is log transformation. As I told, the log transformation can be defined by this type of equation. S, which is the transform value, is equal to C log 1 plus R. R is the input grayscale, C is a constant, and depending on the value of C, because C you can say will control the level of transformation. So depending on the value of C, we will get different type of enhanced images. So one example using log transformation. Here we have a frequency spectrum or Fourier spectrum of an input image, and the region which is lying around the center is not that much clear, but if you take its logarithmic transformation, the information is very much visible now. So the frequency spectrum has been enhanced by using logarithmic transformation. These are the values for C. Similarly, we have inverse logarithmic transformation that will do the reverse job as a logarithmic transformation. Then we have power law transformation. So any power law transformation in general can be defined by this sort of formulation. S is equal to C R to power gamma, where C and gamma both are positive constants, and they somehow affect the quality of enhancement. Okay? So one such example of using power law function, you can see here, this is your input image, that is MRI image, and these are the enhanced image using power law function for different values of gamma and C. So if you look at the B part, that means for gamma is equal to 0.6, C is equal to 1. The C part, again C is equal to 1, but gamma is slightly reduced, 0.4, and then here it is 0.3. So we can see here the quantum of enhancement, how it depends on different values of gamma, and maybe as well for C as well. Type of image enhancement technique is contrast stretching. In contrast stretching, this is mainly used when we want to stretch some portion of image intensity. Okay, so let us discuss some features here. Produces higher contrast than the original by darkening the levels below M in the original image. M is a threshold pixel value, you can say. So darkening the levels below M in the original value or original image, and brightening the levels above M in the original image. So if you look at this diagram, X direction says or show you the pixel values for R, whereas Y is for S, which is the transform value. So small region, I mean starting from here to here, it has been stretched to a very large range. So that is what it is called contrast stretching. Okay? So values below M in the input region or input image, they have been transformed towards the darker side. You can see this is the darker region, and values above M have been transformed to the lighter side. Another type of image enhancement is thresholding, very, very important method, which is most of the time it is used. Thresholding means we generate here some sort of binary information. You see in this plot that values which are below M in the input image, they are simply labeled as 0, and values which are above m, they have been labeled some higher value, maybe 1 or maybe some other higher value. So this is a thresholding. It's either black and white concept, where all values below some threshold, they are kept at one scale, while all values above threshold, they are kept at other scale. See the effect of these image enhancement methods, I mean contrast stretching as well as thresholding. So here, this figure show you basically an image with very poor contrast. You can see here, the image might have been captured into bad weather or where the intensity of light was very poor. So image is not very much clear. It's slightly blurred, or you can say very poor quality image. Now, when this image was processed using contrast stretching defined by this particular function, you can see here the function for contrast stretching, then all pixels lying in this region in the input image from here to here, these two regions, they have been stressed from here to here in this region. So an interval of pixel intensities in the input image have been stressed to here, this point. And the result you can see in the left bottom side, that the result of contrast stretching this input image, and the right bottom side is the result of using thresholding. Okay? And that type of enhancement is called bit plane slicing. Bit plane slicing enhancement is mainly used when we use in case of image coding or compression. Meaning of bit plane slicing, you remember that each pixel, if I take here, let us say 8-bit grayscale image, it means that each pixel intensity may be defined using 8 bits of information. So for each bit, we have some information associated with it in terms of zeros and ones. So here basically we have a virtual plane concept. So the bottommost plane is meant for the pixel values, or you can say intensity values for least significant bit. That is bit 0. That is the least significant bit, and the corresponding value is called, you can say, the bit plane 0. Then we have bit plane 1, bit plane 2. The topmost will be bit plane 7. Because 0 to 7 will be different bit positions. So based on that, it means for a given image, we have total, for a given 8-bit grayscale image, we have total 8 different bit planes, and each bit plane has its own information. So if you look at the importance of these bit planes, you will find that the topmost planes have major information associated with the input image, whereas lower planes have lesser amount of information, the image plane. So at the time of image coding, top planes may be preserved, while information in the lower planes may be discarded. So that's the way how image compression can be achieved. Now if you look at an example, let us have this 8-bit grayscale image. It's a fractal image, and if you look its corresponding 8-bit plane images. So here we have 8-bit plane images. So the top left image is meant for the bit plane image with the most significant bit, and you can see here the quantum of information associated with this particular bit plane image is very, very high than if you move towards the lower bit plane images, whereas the top bottom represent the lower bit plane image. So as you move towards the downward side, starting from most significant bit to next lower significant bit, the quantum of information is decreasing. So this concept may be used for image coding. Now, this is very important point, that is the histogram of an image, because in most of the pattern recognition in image processing, the concept of histogram is used. So first you should understand what is the meaning of histogram for image and what type of processing can be done in histograms for pattern recognition purposes in digital image processing. Now, a histogram of a digital image with gray scales in the range 0 to L minus 1 is defined by this discrete function. HRK is equal to NK, where RK represents the kth gray level, NK is the number of pixels in the image having RK gray level, and HRK is the histogram value for gray level K. So HRK basically represents the number of pixels associated with gray level RK in the input image. Okay. For illustration purpose, let us say we have a 4x4 image block here. The grayscale values in this block are basically 0 to 9. It means any pixel in this block will have value from 0 to 9. Now, if you plot the histogram of this image, then you see in the x direction we have different permitted values of grayscale. So starting from 0, 1, 2 up to 9, because the grayscale range is 0 to 9 here. So there are total 9 different values in the x direction. Then along y direction we have number of pixels associated with each grayscale. But if you recall the definition of histogram, that says the number of pixels associated with grayscale RK. So we are going to plot that histogram. You see in the input block, there is no image pixel with intensity 0. So no number of pixel here, 0 number of pixel. For 1, again 0 number of pixel. But for 2, you can see here, there are total 6 pixels with intensity 2. That is the first one, second one, third, fourth, fifth, and sixth. So that is why you have a histogram for grayscale 2 as 6. So you have plotted a line of length 6. Yeah. Then for pixel value 3, there are total 5 pixels. So you plotted line with value 5. Similarly, you can check for grayscale 4 and 5. So this is the way how histogram can be plotted. Then the point is normalized histogram. So normalized histogram is basically a histogram which is normalized in its values. Why do we use the normalization concept? Normalization is basically used to make it compatible with the concept of probability theory. Because histogram is used, is associated, you will see later that how it can be associated with the concept of probability theory to compute different types of features in an image. So to make it compatible, because in probability theory, probability of any event will vary from 0 to 1. That is why the histogram values are also mapped from 0 to 1. And that mapping is called normalized histogram. Here, dividing each of the histogram at gray level RK by the total number of pixels in the image. So now the HRK, which we have seen here, has been slightly modified in case of normalized histogram, and it is defined as PRK is equal to NK divided by N, where N is the total number of pixels in the image. It simply gives the probability of occurrence of grayscale RK in the input image. So PRK gives an estimate of the probability of occurrence of gray level RK. And you can verify that the sum of all components of a normalized histogram is equal to. Because if you take the probability summation of all RKs, then it will turn out to be 1. Histogram processing, the role of histogram processing is that basic for numerous spatial domain processing technique used effectively for image enhancement, Information inherent in histogram also is useful in image compression as segmentation purposes. So in this particular figure or slide, you can see the images and their corresponding histograms. So here we have a dark image. So here most of the content is slightly black colored. That is why the corresponding histogram is shifted towards 0 or centered around the pixels close to 0 values or lesser values. Whereas you have a bright image where the histogram is slightly shifted towards the bright region of the. Then we have low contrast images and high contrast. Low contrast images are basically those images where the amount of contrast or the range of pixel intensities is limited or small. That is why we have a histogram which is limited within a small region. Whereas high contrast image has a lot of variation in image intensities. So you see here that the intensities are distributed from smaller values towards the larger values. So variation of histogram values or histogram is very, very high in high contrast images over low contrast images. Yes. So this is the main objective of the discussion behind histogram, that the histogram equalization. This is one of the methods through which image is enhanced. And the motivation behind histogram equalization is somehow we increase the variance in the histogram values. Here, if you increase the variance in the image, just like here in this histogram, the variance of the histogram is higher than the low contrast image, then the quality of image becomes better. So histogram equalization basically increases the variance of the histogram. So let us discuss these points. As the low contrast image histogram is narrow and centered towards the middle of the grayscale, look here, it is centered around the middle of the grayscale. If we distribute the histogram to a wider range, the quality of image will be improved, which is visible from the slide. Second, we can do it by adjusting the probability density function of the original histogram, the image, so that the probability is spreads equally. But you see, these, if you look, these are the normalized histograms, and normalized histograms are nothing but probabilities of occurrence. Now, if these probability distribution functions or probabilities can be spread somehow, then we get a corresponding equalized histogram or histogram with higher variance with improved quality of image. So basically the motto or the method to work for histogram equalization, we try to expand the probability density function or PDF of histogram. और कैसे करेंगे इसके बारे में बात करते हैं. So here we need a transformation function which will work on the input probability density functions or input histograms, which are normalized, of course, so that the modified probability density function is spread almost evenly the result. So then we can get an equalized histogram or histogram with large variation. What is the property of this transformation for histogram equalization? Property says that PR is single value and monotonically increasing in the interval 0 to 1. Thus R is from 0 to 1 because they are normalized histogram values, so 0 to 1. Similarly, S will also vary between 0 to 1. And second, that TR, that is, so first it should be monotonically increasing, and the range will remains same. It is not going to change. Maximum value will be 1 and minimum value will be 0. So one way, if you look at the statistical theory, one way of obtaining this type of equalization can be that we use this transformation function T as simply cumulative distribution function of random variable R. R, you can say, is a random variable between 0 and 1, and we are going to equalize this random variable. So one method of equalizing this random variable R can be done through using cumulative distribution function. So for a continuous value of R, we can define this transformation T, which is cumulative distribution function, by simply 0 to R PR W dW, because cumulative distribution function is nothing but the summation of probability density function. If you recall the theory of statistics. So this is the way how transformation can be obtained. Now it's corresponding, since digital images, we work on the digital values, so its corresponding digital definition can be, because PR, if you have learned already, it is nothing but NK divided by N. Then its corresponding cumulative distribution function, that is CDF, will be defined as SK is equal to TRK 0 to K ERRJ. So it is simply the summation of these probability density functions from 0 to K for kth value. The output it's the kth output value. So that is simply the summation of Nj upon N. Now, let us show you the role of histogram equalization, or you can say the importance of histogram equalization. So here, this is your input image. Before histogram equalization, the image was dark. The content was not that much clear. When it was histogram equalized, we got a better image. The image is enhanced, and this histogram is basically equalized histogram. I mean, this is the histogram for this particular image. And if it is visible to you, you can check that the distribution of histogram is near uniform. Note here, it is near uniform. It cannot be pure uniform. It is because of the theta property, because here transformation function we are using is cumulative distribution function. It is the limitation of that particular transformation. Second image, we have a bright side image, but the content is again not very clear. So here, if you perform histogram equalization on this image, we get a better image. Again, histogram is near uniform. So this is the importance of histogram equalization. Through histogram equalization, you learn that we can enhance the quality of an image. Now, one example I would like to discuss, because the topic is very, very important from pattern. Make the concepts, understand it in a better fashion. I'm going to take here an example. Here, RK represents basically the grayscale values. Don't confuse, these are the fractional values. I have labeled it with respect to the maximum value. The first value is 0. Second value is 1 with respect to 7 as the maximum value. Third value is 2. Fourth is 3. 4, 5, 6, and finally it is 7. Because we have measured with respect to 7, that's why we are taking it as 1. Or you can say these are the normalized input values, rather, in that way you can say. And if for this particular image, or for this particular grayscale image, these are the corresponding number of pixels in the input image. It means the number of pixels in the input image with grayscale 0 is 790. With grayscale 1, they are 1023. Similarly, for grayscale 2, they are 850. And this is the way how the distribution of number of pixels for different grayscale values. Then we compute the probability. But if you recall, we need a probability for each grayscale. So PRK is defined as NK upon M. So here we have computed that value. NK is the number of pixels with grayscale 0 divided by the total number of pixels 4096. So the normalized values which we get here is 0.19 for grayscale 0, 0.25 for grayscale 1, 0.21 for grayscale 2, and similarly for others. And you can see, check here that the total sum of these probability distribution will turn out to be 1. Then we compute CDF. It means we are going to perform now transformation for each RK. So transformation कैसे perform कर रहे हैं? We are performing transformation using this equation. SK is equal to PRRJ, where J varies from 0 to K. So if you are going to perform this type of transformation, it means we are going to compute the cumulative distribution function SK. So for 0, it is simply same as probability density function. For 1, it is the summation of probability density function of 0 and probability density function of 1. So 0.19 plus 0.25, that turns out to be 0.44. Then for 2, it is the summation of these three probability density functions. And then for 4, so this is the way how we compute cumulative distribution function. Now once these cumulative distribution functions are obtained, then we map these cumulative distribution function to the corresponding grayscale values. कैसे map करेंगे? We will multiply it by the maximum value of the grayscale, that is L. That is 7 here. If the grayscale is L, so we multiply it by L minus 1, that is 7 here in this case. So we multiply 0.19 by, or rather we normalize with respect to 7. So these are the values, that the transform value with respect to 7. In the next slide, we have taken again the same values which you see here. So, no, wait. So we are taking here the same values once again, this column, and then we are going to convert here, you can say that we are going to basically plot their probability distribution function. कैसे कर रहे हैं? Because the value 1 has been obtained for the input grayscale 0. If you recall here, RK 0 is mapped to 1 in case of output image. So it means there is no 0 intensity value in the output image. So that is why NK are the number of pixels with intensity 0 in the output image are 0. So 0, 0, 0. Then 1 pixel intensity 1 in the output image has been obtained from pixel intensity 0. The 0 has been mapped to 1. Means number of pixels with intensity 1 in the transformed image will be number of pixels with intensity 0 in the input image. So 790, here we have 790 and corresponding probability value 0.19. Then grayscale 2, because no grayscale 2 has been obtained in the transformed image. So grayscale 2 will have no pixel, 0 here. Probability distribution will also be 0. Then grayscale 3 has been obtained from grayscale 1. Or other word, grayscale 1 has been mapped to grayscale 3 in the transformed image. So number of pixels with grayscale 3 in the transformed image will be number of pixels with grayscale 1 in the input image. That is why we have 1, 0, 3 and its corresponding PDF. 4 के लिए there is no pixel here, so it is 0. But for 5, it has been transformed from pixel intensity 2. So number of pixels here are 850. As you see here in the input image, it is 850 in the corresponding PDF value. But in case of 6, since grayscale 6 has been obtained, grayscale 6 in the output image represents grayscale 3 as well as 4 from the input image. In other words, grayscale 3 as well as grayscale 4 in the input image has been mapped to grayscale 6. So in this case, the number of pixels with grayscale 6 will be the number of pixels with grayscale 3 plus grayscale 4, the input image. So it is basically the summation of these two values. Here, the summation, that is 985. And similarly, we can check for 7. 7 has been obtained by using these three grayscales, or these three grayscale values has been mapped to 7 values. So for 7, the total number of pixels will be the summation of these three, 5, 6, and 7. It is 448. And corresponding PDF will be 0.11. Now, if you plot these values, so if you plot these values, you find here that the variation of non-zero values is very, very less than if you compare the variation in non-zero values with the input image. That is what the histogram equation is. Like histogram equation basically converts an input histogram into near uniform histogram. So here these non-zero values are near uniform, though not exactly uniform. And the same concept input image, the corresponding histogram, and there is a lot of variation in the input histogram. But when the image was histogram equalized, the quality of image has been improved and the variation is maximum, or is near uniform histogram. So this is all about histogram equalization. Then we are coming to the concept of filtering. Basically, you can say masking concept. So filters are also used to improve the quality of image or for image enhancement purpose. So there are 4 types of filter you will see. Low pass filter, who pass low information. Okay. High pass filter, high information means high frequency components they pass. Band pass filter, preserve frequencies within a band, and band reject filter, they reject frequencies within a band. You will see that a spatial filter is defined in a neighborhood. As I told, we take sometimes 8 cross 8 neighborhood around a pixel, or we take 16 cross 16 neighborhood around a pixel. So basically the spatial filtering is applied over a neighborhood and an operation that is performed on the pixels inside the neighborhood. समझने के लिए you are going to perform a filtering over this pixel value. So we take here a 3 cross 3 neighborhood, or we may take 5 cross 5 neighborhood. It means we are going to consider, if you are taking 3 cross 3 neighborhood, we are going to consider these 8 neighbors of the central pixel along with the central pixel to find out the region, or to find out the processed pixel value. So let us see how the filtering actually does work. So filter is nothing but a set of coefficients of size. As I told, they can be 3 cross 3 size, 4 cross 5 cross 5 size, 7 cross 7 size. Generally they are odd size filters. So how does it work? Let us say we have a filter where the coefficients are defined as W1, W2, W3 to W9. And this filter is basically superimposed on each pixel at a time. So if it is superimposed on, let us say, this particular point, like here on point Z5, so in this region represents basically the pixel intensities in the neighborhood of 3 cross 3. Because the size of pixel is 3 cross 3. So we are considering here a neighborhood of 3 cross 3. The Z5 is the central pixel, and Z1, Z2, Z3, Z9, these are the neighboring pixels. Then the filtering is performed by multiplying the weights of the filter. These are called the weights or coefficients. So these weights of filters are multiplied by corresponding pixel values on which they are superimposed. So the response of the filter or the result of the filter can be defined by this mathematical formulation, where you can say It is W1Z1 because W1 will overlap Z1, so it is W1Z1, W2Z2 plus W2Z2 and plus up to W9Z9. This is the way how filtering can be performed. Now, if we talk about different type of filters, they are linear or non-linear in nature. It means if the response of the filter can be defined by using linear equation, it is a linear filter. If it is defined by non-linear filter, a non-linear equation, it is a non-linear. Just like here, if you simply take the maximum value of these multiplied coefficients, then that will be the maximum filter. That will turn the maximum value, it may be non-linear filter. Similarly, we have median filter that computes the median values in the neighborhood, minimum filter. So these can be non-linear filters. Next is image smoothing. So image smoothing means that here we basically pass on the low frequency components. So that is why it is called low pass filter. So in the when the filter is working in the spatial domain, it is referred as image smoothing filters. And here the result of image smoothing filter is that it will reduce noise and reduce small details in the image. We'll see later how does it work. And one type of smoothing filter can be a Gaussian filter. Similarly, another type of filter is sharpening filter, which is used to preserve high frequency components in the image. So that's why they are called high pass filter, means edges information which are they are preserved. So highlight fine details or enhance details that has been buried, blurred. And the response of the filter can be positive or negative, it depends on the filter which is being used. One type of averaging filter or smoothing filter can be an average filter. Just like you can see here the coefficient of these filters all are 1, and finally the response is multiplied by 1 by 9 if it is 3 cross 3, 1 by 25 if it is 5 cross 5. That means it is simply the role of these filters is simply it will compute the average value in the neighborhood, and it is one type of low pass filter. So if you look at the response of that averaging filter, here we have the original image, and when these low pass filter, that is averaging filter is applied, where the filter size is 3 cross 3, the result is shown here. And as we increase the filter size, then the major information is preserved, but the smaller information is now slightly removed. Just like if you look at the tungsten wire in this bulb, so if you increase the filter size, the tungsten wire is not that much clear here. And if you further increase the filter size, the image becomes blurred, and only the large amount of information or the information which is the large contributes more will be preserved, and the remaining is simply blurred. So you can see here, if you increase the filter size up to 25 plus 25, it only show you the outline of the bulb, whereas the most of the details are now clear, not clear. They are not available here. So if you perform thresholding over this particular image, only the outline of the bulb is available. So this way you can find the shape of this particular object. That's the role of different type of filtering. Another application or another example of using averaging filter is, we have a picture of here sky, where we have small size stars as well as large size stars. Then the image has been blurred by using 15 plus 15 averaging filter. So you can see here the small details are now neglected, and then a thresholding was performed where pixels with one threshold value they have been preserved, and pixels with below that threshold value have been discarded. So you can see that now you can, the large stars are very much visible, whereas the smaller stars have been discarded. So that is the way how averaging filter, a smoothing filter can be utilized. As I told, Gaussian filter is also a smoothing filter, and this is the way how Gaussian filter can be defined. If you recall, this equation represents a Gaussian equation, a Gaussian function, where x, y here will be the coordinate values, and sigma represents the variance value. So for different sigma values of sigma, we can have different filters. This filter has been obtained of size 7 cross 7 with the variance value as 1.4. And the filter may be used for image smoothing purposes. Similarly, this is again 15 cross 15 filter is sigma S3. As I told, median filter is basically a non-linear filter that computes the median value in the network. So such filter is very, very effective for noise removal, and especially the noise is salt and paper noise. So here you have an input image, and the image has been corrupted because of salt and paper noise. Salt and paper noise means real life noise. And then averaging is performed, or any average filter was applied on this noise image to enhance its quality. Then you can see, though image has been improved slightly, but not that much, content is not that much clear here. But if instead of using averaging filter, if median filter is applied on this image, you can see there is a drastic improvement in the image. The median filters are mainly used for noise removal, and they are also used in image reprocessing, pattern recognition. So in this slide, you can see how the median values are computed. So in the neighborhood, we have taken here 3 cross 3 neighborhood. So all 9 values are first sorted out, and then the median value is chosen, and that median value is used to replace the central value. So you can see here, most of the pixels, in fact, all 8 neighbors are having values close to 0, whereas the central value has 99, it means it's a sort of noise. So by using median filter, the 99 value has been replaced by its median value, which is 20. The noise has been discarded. Similarly, we have high pass filter. High pass filters are mainly used to preserve edge information, or whenever there is sharp change in intensity values. And one such type of filter is this one, that is sharpening filters. And the response is non-zero whenever there is transition in the intensity value. For example, when this filter is applied on this segment of image, so in this region where the intensity values are almost uniform, all are 10, then there is no change, and response is, there is no change actually, and the response is near 0. When this filter was applied on this region where there is a transition from 10 to 80, then the response is non-zero. You can see the importance, the role of sharpening filters. Here we have input image, moon, this is the image of moon, and when it was applied, sharpening filter was applied, then we can see the effect of sharpening filters. Depending on the type of sharpening filters, we have different type of images here in the output. So you can see the edge information is very, very clear in these sharpening filters over this one. As you can see, this portion is slightly blurred. The input image is very, very clear here in the output image. Okay, let me skip this. Right. Now, sharpening filters are obtained by computing the gradient of an image. We find basically the derivative of an image to compute the sharpening filters, or to generate sharpening filters. So derivative of an image, where we denote image by f, can be computed using a gradient value. And this gradient value f, grade f is defined as del f for del x and del f for del y. So you can see that the gradient value is nothing but it's a vector value, and the magnitude is defined by this way, and its orientation is defined in this way. It is simple vector mathematics. And the role of derivative is that magnitude provides the information about the edge step, because as I told, that gradient is one way to generate sharpening filters. So the quantum of magnitude represents the sharpness of the edges. The more magnitude, the more sharp the edges you will have, or strength of the edges will have. And the direction of edges can be identified by using the direction of this gradient value. So basically, if you compute the gradient at some point, then this gradient direction will be a perpendicular at a normal vector against the direction of the edge. So this is the way how direction of edges can be controlled or can be identified. So one such filter, I'm going to come to discuss some sharpening filters. Before that, let me see the importance of partial derivative with respect to x and partial derivative with respect to y. So here you have input image, which we denote by function f. And when this image was derived, it is partially its partial derivative with respect to x is taken, then we can see that in case of both, whether it is partial derivative with respect to x or with respect to y, in both cases we get as information, or whenever there is change in intensity value, we get that information here. But you compute partial derivative with respect to x and plot the result, then here we get the vertical edges. You can see here the vertical edges are more prominent if we take partial derivative with respect to x. Whereas if we take the partial derivative with respect to y and plot that image, then we have horizontal edges are prominent here. So some filters which are used to compute derivative, you can say they are basically Robert filters. You can say these are the filter coefficients for Robert filter. It means when this filter is convolved around an image, we will get a gradient image with respect to x. When this filter is convolved in the image, we will get gradient image with respect to y. And if you club these images, or if you combine their values, del f over del x whole square plus del f over del y whole square, we will get basically the final gradient image. Similarly, we have Prewitt filters and Sobel operators or Sobel filters to compute gradient images. Note here, these gradient images are meant for the first order derivative or first differential image, first order differential image. Similarly, we have second order differential images that are also. So once again, this the input image, the partial derivative with respect to x has been plotted here, partial derivative with respect to y have been plotted here, then the magnitude values obtained by this formula is plotted in the result. So you can see here that edges information are visible in the final image. Last, here, another type of gradient operator is Laplacian operator, that is second order derivative. Though the previous discussion, previous derivative were the first order derivative. So second order derivative is also used for edge detection purposes. So one of the one such filter that is second order derivative is called Laplacian filter, and the coefficients for Laplacian filter are defined in this fashion for 3 class 3 filter. They are also used for edge detection purposes. Now you can see here the difference between the first order derivative image and the second order derivative image. So here you have input image, And then when the S detection was obtained by using Laplacian derivative or second order derivative, the image is this one. And when the Sobel operator first order derivative is performed, corresponding image is shown here. Both type of derivatives are used for identification of images, though they have some pros and cons that may be you can check from different literature available in image processing domain. So this is all about the fundamental of images. Going to use this concept for one type of medical image processing application, which is a pattern recognition in medical image processing. Give me 1 minute time. I'm coming back. Give me just 1 minute time.
Okay, sir. Okay, sir.
Hello, am I audible?
Yes, sir. Yes, sir.
So we are going to discuss now one application of pattern recognition in image processing. That is basically a content-based image retrieval. Here, basically, what is content-based image retrieval? Here, images are retrieved, or similar images are retrieved from a database of images. So, in fact, we have here a query image, which is an unknown image to the database. So, an unknown query image is given as input, and this query image is classified to the best matched images from the database. कैसे काम करते हैं? How does it work? So this gives you the general diagram. I repeat, it's a general diagram for any content-based image retrieval system. Here we have image database, and here we have a query image. So actually, this image database is defined, and the images in the image database are defined with the help of certain features. These features should be different type. I mean, there should be scale invariant, there should be translation invariant, rotation invariant. So such features are used to define those images. So those features are extracted, and obviously these features are stored somewhere in the file. And when query image is produced before the system, before the content-based image retrieval system, again those features are retrieved from the input query image, and then these feature sets are compared with the feature sets available in the image database. Okay? And as far as comparison is concerned, it can be a one-by-one comparison based on some distance metric based operation, or it can, here we can use some sort of classification approach, like neural network or any other type of classification, SPL like that. And those images which are very much similar to the feature set for the query image, they are retrieved. So here this is the way how the images are finally obtained. So here I'm going to discuss about shape-based features for classification of lung CT scan images. So this is in this particular research article, you can consider this one, the source one is the source of this particular article. And if you are interested in detail about this technique, you can download this paper and check it out. So here basically we are going to detect different type of CT scan lung CT scan images from image database. And the description, as the name suggests, the description of images are defined with respect to some features which are shape-based features that define the shape of the lung region, cancerous region. So let us discuss some features that have been taken to define an image. Here 4 local features have been chosen and 2 global features have been chosen. Local features means since we are going to detect here the quantum of cancer, lung cancer in different regions, so what we do, we just a minute, yeah, before let me discuss this slide first. So we have a query image here, and then this query image is segmented through image segmentation techniques, and we identify some contour regions in that query image. These contour regions are likely regions, are the regions which are likely to be the cancerous regions in the image. And once these cancerous region or possible cancerous regions have been segmented, then these features are extracted for those cancerous regions. And these features like solidity, it is solidity, not solidity. Solidity, circularity, HOG, that is a histogram of oriented gradient, and DFT of that discrete Fourier transform of radial. So these 4 local features have been extracted from those possible cancerous regions, and 2 global features means these are the features which are obtained from the image itself. First 4 features are meant for particular region, whereas these 2 features are meant for the entire image. So the moment feature, that is the second order moment, has been computed. The various order of moments, and second order moment, which represents the variance in the image, that is taken, and histogram of the image, which you are aware of the concept histogram, that is also been taken. Now let me explain these features. Before coming to that, we have taken here 2 databases which are widely available and they are used by research community. One is Emphysema database and there is LCAP lung database. So they are available. One can download those databases. So how does the proposed works here? Those 6 features have been extracted. It means each image in the database has been associated with these features or has been defined with the help of these features. And similarly, the query image has also been defined with the help of these features. These features are given as input to a convolutional neural network. You might have read that convolutional neural network automatically extract features. I agree, but the method can be modified where we can give some external feature. They are called handcrafted features to a convolutional neural network to perform classification. And then we have the final image classification of the query image. Now, let us understand the proposed work step by step. So first point, as I told, that the extraction of mass contour region in the image. So this mass contour region extraction is done by using a model which has been proposed into this particular paper. I was sharing data in this paper. And here, basically, this detection of contour is basically an optimization problem. And you can see here that the contour detection or contour is identified by this particular function, and this function is optimized with respect to these 3 variables, that is theta, beta, and lambda. And you can check the details here in this particular reference, that how does it work. So by repeating, by iterating this function for different values of theta, beta, and lambda, or in other words, by fine-tuning these different values, we optimize this function, and once the function is optimized, it will generate the contour region in the image. So once the contour region is identified, then we create a convex hull around that contour region. Reason is why we generate convex hull, because to define solidity feature we require the contour hull concept. So what is contour hull? For example, this your region which has been extracted by that model, say snack model, that is called snack model, and then convex hull around this region is to be identified. Convex hull means, or convex region means, this is the region in which if you take any 2 points and connect those 2 points will lie within that region. That is called convex region. And this convex region should be as tightly, it should cover as tightly as possible to the this particular construct region or mass region. Make it very much to define its complete or clear shape of that particular region. This is the way how contour region or contour hull can be identified. So contour hull has been identified. Then the next step is, then we take n different points on that hull or on that region defined as xi, yi, and we compute solidity feature. How does it computed? It is computed by the ratio of the contour, means the mass construct region, divided by the area of the convex hull. Okay? So A, that is the area of the active contour, and divided by H, the area of the convex hull enclosing that particular contour. So this feature will represent the solidity feature. Ideally, the value should be 1, because if the convex hull covers is as tightly as possible, the hull will be very much similar to that region and the area will be same. So maximum value for solidity function is 1, otherwise less than 1. Area can be computed. You are all aware that by using discrete endpoints, we are computing area piece by piecewise. So piecewise area is computed, and you can verify it because the points will be considered twice. That is why the area is divided by 2. Next feature is circularity feature. It detects how circular is the region in, say, means whether it is exact a circular region or how close it is to a circle, and that can be defined by using this function. So quantum of circularity of that region is measured, and it is 4 pi a divided by p square, where a is the area of the contour and p is the perimeter of the contour. This is the way it can be computed. Third point or third feature is discrete Fourier transform coefficients of radial length function. So first point is how to compute radial length function. So for compute radial length function, basically first we compute the centroid of the contour, that is xc and yc. So xc, yc represents the centroid of those endpoints that we have considered. And once that centroid has been identified, then for ith point we compute the Euclidean distance from the centroid. So that is why R is defined as xi minus xc whole square plus yi minus yc whole square. Because they are endpoints, so I vary from 1 to n. So this way we get total n radial points. Okay. Once these n radial points have been identified, then we compute their discrete Fourier transform values. And you are all aware of discrete Fourier transform, how it is computed. It is simply one-dimensional function here in this case, or one-dimensional transformation. So again, we will get n discrete Fourier coefficients. So it means the third feature set is these n discrete Fourier transform coefficients. Then the fourth is a histogram of oriented gradients. This is very, very important feature in most of the image processing based pattern recognition. You all are aware of the histogram. How the histogram is computed? Then yahan par what we do, we compute basically the histogram of oriented gradients. So what is the procedure? Let me discuss here. Basically HOG defines the shape of objects present in the image in a better fashion. And to compute it, image is broken down into 16 cross 16 regions. They are called image blocks. because it has been scientifically proved that if the images are broken 16 plus 16 regions, the result is better. That's why 16 plus 16 regions have been taken. And the gradient and orientation are computed for each of these regions. So gradient कैसे compute करते हैं? We basically compute the gradient image of the input image, and then we define, or we divide rather, the entire gradient image into 16 cross 16 regions. Okay? And then since gradient is a vector, then we compute the orientation at each point by this way. So Ix and Iy are the components of gradient values. So gradient magnitude is computed as well as its orientation is computed. And the histogram is generated for each of these regions separately, which is then concatenated. It means the histogram of these orientations are computed. So note here, it is the histogram of orientation, not histogram of the magnitude. So orientation is computed, and then all histograms of these blocks, 16 plus 16 blocks, is concatenated, and that forms one feature vector, that is the HOG of the input gradient, oriented gradient. So that is one feature. And finally, two global features, and one is the histogram of the image, that's a vector of length equal to grayscale of the image, and moment of the entire image, which is the second order moment we have taken. So if you remember how the second order moment can be defined, it is Ri is the ith gray level, M is the mean value in the image, our expectation value in the image. So Ri minus M whole square multiplied by Pi, where Pi is the probability of occurrence of ith grayscale, Rith grayscale. So it is nothing but variance formulas. Using these 6 features, image is classified. So now classification point, how it is done using CNN, convolutional neural network. We have slightly modified a convolutional neural network here, which was already proposed by someone. Here, the layers, if you look in this figure, this is basically the architecture of convolutional neural network. Most of the convolutional neural network that are used for lung cancer detection, they are very complex in terms of number of layers and their connections. Here we have proposed a very simple CNN consisting of only these many layers. So you see here, one is the rectilinear ReLU layer, max pooling layer, dense layer, and followed by classification layer. We are not using any convolutional layer because handcrafted features have been given. Convolutional layer, the role of convolution layer is to identify features in an image. Okay? And since features have already been extracted, so convolutional layer is not required at all. So, and some parameters that have been used here, ReLU layer, if you take the pool size, I'm sure that you are aware of the meaning of these. It is 1 class 1, and stride value is again 1 class 1, and no convolution has been taken because external features are extracted. So using these features, finally classification layer performs classification. Now if you look at the performance of the proposed model and compare the performance with other models, the performance is quite much appreciable. But let me show you some results, intermediate results. This was your original image from Infosema database. It has some cancerous regions here, you can see. And these cancerous regions have been segmented, or mass contour has been segmented by using that model, SNAP model, and where the result is shown through after 10 epochs, as I told. If you recall this function, so here this function is optimized for each iteration. So after 10 epochs, the region is something like this. And then we compute here some parameters. And then of course we extract features for these contours. We have discussed 6 features. and then using those features, classification is done. Now, classification and the performance is measured with respect to some parameters like recall values, precision values, and we have accuracy. So these are three parameters that have been used to measure the performance of the proposed model. And if those who are not aware of how these recall values, precision values, or accuracy is computed, you can understand through this slide. Let me explain you through this slide. Here, let us say your model or your database has only two type of patterns or two class patterns. One is, let us say, positive, and that is negative class. And here in the along x size or horizontal size, this is the pattern class which has been predicted by the model, and along y side this is the pattern class which is actual class of the patterns in the database. Then we use some terminology here: true positive, false positive, false negative, and true negative. What is true positive, true false, and these parameters? True positive means that a pattern which was in positive class has also been predicted into the positive class. That is a true positive value. Similarly, if a pattern which was actually in the positive class or class 1, but it has been misclassified to the model into class 2 or into the negative class, this type of error, of course, the error, this is called type 2 error, and terminology is false negative. Okay, and there is false positive, where a pattern which was, let us say, negative, or a pattern of one class has been classified. Here you see that false negative, false positive is actually, it is for the negative class, but predicted model has identified that pattern into the positive class. So it was from class 1 but has been misclassified into class 2, that is false positive. And true negative means those who are not part of class 1 class or negative class, they were also classified into negative class, that is true negative. And then using these four parameters we compute precision. So precision is defined as true positive divided by true positive plus false positive. You see here that if false positive is limited, if it is limiting towards 0, then precision will be 100%. If the error turns to be 0, then the precision is 100%. Other parameters like sensitivity, that is true positive divided by true positive plus false negative. Sensitivity is also called recall value sometimes. And accuracy is computed by using this way: true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. So if you compute the recall value, for different databases, so here the performance is shown. For in FISHIMA database, basically the entire database was divided in 4 classes or 4 categories of cancer. So we have total 4 groups: group 1, group 2, group 3, and group 4. And for each group, the proposed model, the recall value, actually the recall value should be maximum, precision should be maximum, accuracy should be maximum for a better model. So we can see here that for the proposed model, recall value is more than existing models. And these models are very much, they are very recent models for lung cancer detection. Similarly, for the same database, if you compare in terms of precision value, again the proposed model performs better. Then for another database, that is LCAP database, here there are total 10 possible states of cancer. So the image has been categorized into 10 groups, and the performance is measured with respect to recall value for the proposed model, and for the precision value, and finally it is the accuracy here for both data sets. So it's an average accuracy value. So for emphysema database, close to 90.80%. And for LCAP database, 94.1%. So this is the way you can understand how the concept can be used. Now, if you want to look at this model, which was used to identify the contours in the image or passport cancers region, paper can be downloaded from this particular source. So this is all about today for this particular session. If you have any question, you can now ask.
Okay, sir. Any queries from the participants? Okay, I think. Yes. Any queries from participants? Very good, sir. You have nicely explained, and I think already all the doubts are cleared. So I think yes, no doubts from any participants. Okay. So I think it is the time of vote of thanks, sir. Thank you very much
Thank you.
for
Thank you
giving
very
a
much. Thank
wonderful
you.
session. So, on the behalf of SSBT CVT Bambhori, Jalgaon, and Department of Electronics and Telecommunication, I thank you very much, sir, for giving a wonderful session, as well as you have given a lot of idea about the image processing, as well as how to club all these things together. Okay. So I also thankful to Dr. Girish Patnaik, sir, who is the HOD of our computer engineering department, who have given reference of Dr. Ravindra Purwar, sir. So
He was my classmate after.
yes, sir. He told me, sir, that we were friend, and he will accept your request. So that's why, sir, you have accepted our request from your busy schedule. So I'm thank you very much, sir, and as well as I thank from Girish Patnaik, sirs, also. So I hope very good session you have given, sir. Thank you very much, sir.
Thank you. Thank you.
Okay, sir. So we'll meet, sir. Sir, please share these slides, sir. So some of the participants are asking that. Please share that slide, sir.
नहीं तो फिर मैं आपको मेल कर दूंगा आई
Yeah,
थिंक मेल
yeah. No problem, sir. You just mail me, so I will share it over the group. Sir, one participant is asking that convolutional neural network lies in which type of learning, supervised or unsupervised?
अच्छा actually yeah convolutional neural network they are basically supervisor, they are basically artificial neural network with level data, they are useful for level data. Okay, hello.
Yes, sir. Yes, sir.
I mean the candidate can switch.
Ajay, is your doubt is cleared? Ajay Patankar, please turn on your mic.
Yes, sir. Clear, got it,
Yeah.
sir. Thank you.
Yeah.
they are useful for level data. Okay, so it means it's supervisor.
Okay, sir.
Okay. Thank you very much, sir.
Thank you.
Yes, sir. Yes. Okay, sir. So dear all participants, now it's a time for lunch break. So we will meet at 2:50 sharp for the third one session with Bipul Kumar Shahi. So thank you very much. We are just terminating this session, and we will rejoin. You have to rejoin it again at 2:50 only. Okay. So just we are terminating the entire link. Okay. Thank you all the participants.